Hello and welcome to High Voltage Engineering. We'll be talking about measurements of high voltages and currents. We have in the previous module we have discussed about the production of high voltages and currents. Now we are talking about them how to measure the high voltages and currents. Okay. Now the topics we will be covering here is that we are going to cover the measurement of high indirect current voltages, that is DC voltages. Then we will be talking about high AC voltages as well as impulse voltages. Then we are going to see the measurement of high DC current. Then we will talking about the alternating and impulse currents. Okay, then we will talk about the cathode ray oscillograph for impulse voltage and current measurement. So the last part we will be seeing how the oscillographs is used for the impulse voltage as well as the current measurements. Okay, so let us start with module 3.1, where we will be talking about measurement of high DC current voltages or high DC voltages. Okay, now in the high DC voltages there are certain 5 types of measurements of DC voltages. One is high ohmic series resistance with microammeter. Second is the resistance potential dividers for DC voltages. Third is generating voltmeters. Fourth is measurement of DC and AC electric fields. And fifth one is measurement of ripple voltage in DC systems. So the first one is a high ohmic series resistance with microammeter. This is the basic form of a DC voltage measurement. Okay, now again we have a resistance potential dividers for DC voltages. We have generating voltmeters. Now we will be measuring AC with AC and of DC with an AC electric field. Next we will talk about the ripple voltages, that is if you have in all the DC we come across, we do not actually experience a pure DC, we have some ripples in there, so we will be measuring the ripple voltages in the DC system. Okay, so the first topic, high ohmic series resistance with micrometer. So the basic system is given on the right hand side. So we have this resistance which is connected to high voltages. We have a microammeter, and we have a protective device. Now what it does is that the most of the resistance, the most of the high voltage is actually being taken or being eaten up by the resistance itself. So the microammeter actually gets a very small amount of the current. Okay, basically it is a ammeter which is used to find the voltage across the high voltages. You have to adjust or calibrate the microammeter in that fashion. So we can say that the high DC voltages are usually measured by connecting a very high resistance, a few hundreds of mega ohms, in series with a microammeter. The voltage drop in the meter is negligible as the impedance of the meter is only few ohms compared to few hundred mega ohms of the series resistance R. The ohmic value of the series resistance is chosen such that a current of 1 to 10 microamperes is allowed for the full scale deflection. So you have only 1 to 10 microamperes. So accordingly you have to set that resistance. What is the resistance to be kept in series? A protective device like a paper gap, a neon glow tube, or a Zener diode with a suitable series resistance is connected across the meter as a protection against high voltages in case of series resistance R fails or flashes over. So there is a protective device for the microammeter. The resistance is constructed from a large number of wire bound resistors in series. Now there are certain limitations for the series resistance microammeter. One is the power dissipation and the source loading. So there is a lot of power dissipation there, so you get a lot of heat, and the source will be loaded. The way the amount of the high voltage which you are measuring that is produced by a certain source. Now the source will be loaded because of this equipment, because it has this high resistance. Okay, the temperature effect as long and long time stability. So again the temperature will rise and the stability might be compromised if you connect it for a long period of time. Voltage dependence for the resistive element. So this resistive element is dependent on the voltage, so accordingly depending on the voltage we are going to measure, the range of voltage we are going to measure, we have to connect the resistance R, so that we have a deflection between 1 and 10 microamperes. And the sensitivity to mechanical stress. So if there is some kind of mechanical stress, this is the very microammeter is a very sensitive device, okay, that may not be efficient in case of any mechanical stress. Next part is the resistance potential dividers for DC voltages. Okay, what it does is that it splits up the voltage using potential dividers. The influence of temperature and voltages on the element is eliminated in the voltage divider arrangement. So what we have seen previously, it is now been eliminated. The high voltage magnitude given by R1 plus R2 divided by total by R2 into V2, where V2 is the DC voltage across the voltage arm R2. Okay, so we are splitting as for the potential dividers, we are splitting the voltages using the two different resistances R1 and R2. With sudden changes in voltage such as switching operations, flashover or of the test object, or source short circuits, flashover or damage may occur to the divider elements due to the stray capacitances across the elements and due to ground capacitances. So sudden voltage change is not desirable here. To avoid this transient voltages, voltage controlling capacitors are connected across the element. Okay, so you have a voltage controlling capacitor to remove this stray transient voltages, and a corona free termination is also necessary to avoid the unnecessary discharges at high voltage ends. So we are talking about the resistance potential dividers for DC voltages. Of this we have for the same application for the high voltage DC HVDC dividers for HVDC transmission systems. Similar we use for the HVDC transmission system. So in this case, the DC voltage measurements in HVDC transmission systems, the voltage divider is used should measure a steady DC voltage, be a ripple voltage, and any transient voltages. The resistance component of the divider is made of high precision low inductance component resistors connected in series as needed for the primary voltage and defined current, usually 1 milliamperes to 0.5 milliamperes. Grading capacitors are connected in parallel to the resistors to facilitate ripple measurement and also protect against high transient voltages. Next we will talk about generating voltmeters. Now what happens here is that the high voltage measuring devices employ generating principle when source loading is prohibited, as with the Van de Graaff generators. So when you connect previously voltmeters, we are actually loading the source. That means what, you are connecting a load to the source now, because you have a high resistance you are connecting across the according the source. So when that is not allowed, we create a voltmeter that generates the voltage. So high voltage measuring device employ generating principle when source loading is prohibited, as with the case of Van de Graaff generators, or when direct connection to the high voltage source is to be avoided. The generating voltmeter is a variable capacitor electrostatic voltage generator which generates the current proportional to the external voltage. So what we have is that we have a variable capacitor which creates voltages. So there is no direct connection, rather the voltage is generated, okay, by induction of the charges. Like for example, we have this voltage. If we bring an metal plate close to that voltage source, that metal plate will act as a capacitor now. So the capacitor getting charged, and that it generates a current that proportional to the applied voltage. Okay, the device is driven by an external synchronous or a constant speed motor and does not absorb power or energy from the voltage measuring source. Now we'll look at the principle of operation of generating voltmeters. The charge stored in the capacitor of the capacitance C is given by Q equal to C into V. We know this. If the capacitance of the capacitor varies with time, when connected to the source of voltage V, the current through the capacitor is given by dq dt, or that is nothing but V dc dt plus C dv dt. Okay, we previously have seen this current in terms of C dv dt, but since the capacitor is also variable, we have to use this term V dc dt. Okay, so for a DC voltage dv dt is 0, so we have I is equal to V dc dt. Okay, if the capacitance varying between a limit of C0 to Cm sinusoidally, we have C equal to C naught plus Cm sin omega t, which produces a current of Im cos omega t, and this Im is nothing but V into Cm omega. If Im is the peak value of the current, the RMS value of the current is given by this Vcm omega by root 2. So if you remember your circuit theory, the voltage across the capacitor is given by C into dv dt, but here since the capacitor is also changing, we use V into dc dt plus C into dv dt, but here there is no change in the voltage, rather the capacitor changes. Now depending on the change in the capacitor, we are getting the current, and hence the current is given as V dc dt. Okay, so for a constant angular frequency omega, the current is proportional to the applied voltage V. More often, the generator current is rectified and measured by a moving coil meter. Generating voltmeter can be used for AC voltage measurements and also provides the angular frequency omega is the same or equal to half of that of the supply frequency. Now we'll see about the construction of the generating voltmeter. A generating voltmeter with a rotating cylinder consists of two exciting field electrodes and a rotating two-pole armature driven by a synchronous motor or a constant speed n. The AC current flowing between the two halves of the armature is rectified by a commutator whose arithmetic mean may be calculated from this equation given below. For a symmetric voltage, C minimum is 0. When the voltage is not symmetrical, one of the electrodes is grounded and C minimum has a finite value. The factor of proportionality delta C is determined by calibration. This device can be used for measuring AC voltages provided the speed of the drive motor is half the frequency of the voltage to be measured. Okay, so this on the right hand side, this is a construction of the generating voltmeter. So you have different capacitor discs which are controlled by the motor. So depending on the amount of capacitor disc coverage, we are getting different value of the capacitor. Okay, and this different value of the capacitor will create different values of voltages. Okay, generating voltmeter employs rotating sectors or vanes for variation of capacitance. So you can see you can have different vanes or rotating sectors given on the right hand side. The high voltage source is connected to a disc electrode S3. You see S3 being shown there, which is kept at a fixed distance on the axis of the other low voltage electrode S0, S1 and S2. The rotor S0 is driven at a constant speed by a synchronous motor at a suitable speed 1500, 1800, 3000 or 3600 rpm. The rotor vanes of S0 cause periodic change in capacitance between the insulated disc S2 and the HV electrode S3. The shape and the number of vanes of S0, S1 are so designed that they produce a sinusoidal variation in the capacitance. The generated AC current through the resistor R is rectified and is read by moving coil instrument. An amplifier is needed here. If the shunt capacitance is larger or longer leads are used for the connection to rectifier and meter. The instrument is calibrated using a potential divider or spear gap. The meter scale is linear and its range can be extended by extrapolation. So this is a description of the generating voltmeter construction. Now we'll talk about advantages of generating voltmeter. There is no source loading here, no direct connection to the high voltage electrode. So two are very important. There is no direct connection and source is not loaded. Scale is linear and the extension of range is easy. A very convenient instrument for electrostatic device such as a Van de Graaff generator and particle accelerators. Now it has limitation that they require calibration. Now carefully construction is needed and is cumbersome instrument requiring auxiliary devices. So you need a motor to run the capacitor. Disturbance in position and mounting of the electrodes may make calibration invalid. So you have to be mounting this motor and the capacitor very minutely and very accurately, or else any change in the mounting will change your calibration. Now we talk about measurement of DC and AC electric fields. Electric field exists in the near vicinity of very high voltage power line, extreme high voltage substation and other power apparatus. At present, the EHV and UHV transmission system with rating of 750 kV AC and higher and 500 kV and higher have become very common. People throughout the world are more concerned about the electric field on account of their biological and ecological effects and possible shock hazards. Hence, the development of electric field meters and measurement of electric field have become essential. So, since we are now transmitting voltage at transmitting power at a very high voltage, so it has become essential nowadays to measure the electric field, because this high voltage will create a huge electric field and that might affect the biological and will have an ecological problem. Okay, so we need to measure the electric field, so the electric field measurements is needed. So we have this DC electric field strength meters. The electric field strength meters can be measured using there are two ways of measuring that: using a variable capacitor probe or generating voltmeter, and two, a vibrating plate capacitor. So we have a variable capacitor probe and a vibrating capacitor. Now let's talk about the variable capacitor field meter. If a metallic electrode is kept at in an electric field E, the total charge induced in the surface is given by Q, that is equal to epsilon E A into E, that epsilon is the permittivity and area of the cross section, and E is the electric field. The A can be said as this we can say that can be equal to epsilon integral of E dA. If the area of the sensing electrode varies and the variation of the area of the sensing electrode is periodic, then the current flowing through the measuring electrode is given by I dq dt, that is nothing but Q max minus Q min by T. So the average electric field is nothing but Q max minus Q min by epsilon AT. Okay, so it is nothing but equal to I by epsilon A if you have a Q min to be 0. That means you assume the minimum charge to be 0 charge. So we can get the electric field if we know the current, and we divide it by the epsilon and divided by the area, will get the electric field. So we have this variable capacitor field meter. Okay, so we are measuring here is, again we have a motor that we have a variable capacitor and that are placed in the electric field. The motor is rotating with the speed of omega. And now we are going to measure the current in the capacitor, and from that current we are getting we'll get the value of the electric field. The sensing electrode, which is in the form of a circular disc, is divided into sectors and shielded by the rotating shutter, which rotates at an angular velocity omega. The shutter is driven at a constant speed by a motor. Two opposite sectors of sensing electrodes are grounded. You can see the grounding there in the right hand side diagram, and the other two are connected to the ground through measuring resistance R. Okay, the voltage across the resistance is measured, and from this electric field intensity E is determined. The induced current signal voltage is rectified by a phase sensitive detector operating with suitable phase angle relative to the movement of the shutter and is calibrated in terms of electric field E. So we have seen the previously variable capacitor system. Now we will be seeing the vibrating plate field meter. In this meter consists of a fixed plate with an aperture. So you can see a fixed plate with an aperture, that is a space between this fixed plate. This, due to the vibrating motion of the driver plate, a variable voltage K between the two plates, that is the face plate and the vibrating plate, is generated. Okay, so what we are doing is that we are creating a vibration through the mechanical modular driver. You can see. Okay, this essentially a variable capacitor, and electric field is proportional to the voltage generated. So since this we are creating a variable capacitor, depending on the electric field we'll get this different capacitance, and that from that we can measure the voltage. The instrument is calibrated by placing it in a known electric field. So the AC field strength meter, we will be talking about a capacitor probe. So the electric field capacitor probes are shown here, different types. We have a spherical and we have a parallel plate. Both of these are in terms of capacitance. Okay, the AC electric field is usually measured by introducing a small fixed capacitance probe into the field area and measuring the induced charge on it. So we have these different probes. Now these probes are used to measure the AC field. Previously we were talking about the DC electric fields. Okay, now we'll talk about the AC electric fields. Since the electric field between the plates of the capacitor is proportional to the charges induced in the plates of the capacitor and varies because of the variation of the AC field, electric field, the capacitance current is measured for the field. The charge Q is induced on the surface of the conductor of in an electric field E for a spherical electrodes given by Q equal to 3 pi a square epsilon 0 E, that is nothing but K into epsilon 0 E. So the charge that is being collected will be proportional to the E. The RMS value of the current is proportional to E. Depending on the type of the probe electrode used, the value of the K is determined and is included. The current is usually measured through a rectifier meter. This meter can be used over a wide range of frequencies but must be recalibrated for that frequency. The accuracy of the meter is about 0.5% and depends on the harmonic content, atmospheric conditions like temperature, humidity, etc., and the position or location of the meter in electric field. If the electric field in an AC is given by E sin omega t, the current through the probe will be I equal to K omega epsilon 0 E cos omega t. So we have seen how to measure the AC electric field. Now we will be talking about measurement of ripple voltage in DC systems. So we have known previously that the ripple voltages are seen in DC because not all DCs are pure, so you have different ripple voltages, so you need to measure these ripples. The ripple voltages are AC voltages on non-sinusoidal nature and such as oscillographic measurement of these voltages is desirable. However, if the resistance potential divider is used along with an oscilloscope, the measurement of small value of the ripple that is delta V will be inaccurate. So potential dividers are not useful here. A simple method of measuring the ripple voltages is to use a capacitance resistor, that is CR circuit, and measure the varying component of the AC voltages by blocking the DC component. So if you use a capacitor resistor system, you are basically blocking the DC component, as the capacitor will not allow a DC to flow through it. If V1 is the DC source voltage with the ripple and V2 is the voltage across the measuring resistance R, with C acting as the blocking capacitor, then V2 is nothing but V1 minus VDC, that is the ripple voltage. So in the right hand side we are seeing the circuit arrangement for the measurement of a ripple voltage. Okay, now we can measure the ripple voltage with a CRO. Here the capacitance C is rated for a peak voltage. It is proportional to the switch S and to be closed when the CRO is connected to the source, so that CRO input terminal does not receive any high voltage signal while C is being charged. Further, C should be larger than the capacitance of the cable and input capacitance of the CRO taken together. So this is the end of this lecture. Thank you.